Okay, so here we're working with a system. It just has 1 kilogram of water, and we're undergoing a so-called power cycle consisting of the following processes. So we have 1 to 2, 2 to 3, 3 to 4, and 4 to 1. We're asked to sketch the TV and PV diagrams, and we can neglect kinetic and potential energy, and we're also going to look for the thermal efficiency. So obviously there's a lot going on here, a lot of variables to keep track of, so I'm going to organize everything into 2 tables here. So I have 1 table for each of the processes, 1 to 2, 2 to 3, and so on, and then I also have a table for every single state with every property at each state. So the best thing to do is to start off by filling in what we're given. So for process 1 to 2, we have a constant volume heating from P1 equals 5 bar, so I'm going to go ahead and fill it into here. So we have 5 bar, T1 is 160 C, P2 is 10 bar, and then we're told that 2 to 3 is a constant pressure cooling to a saturated vapor. So you have constant pressure 2 to 3. So that means that P2 to P3 is going to be 10 bar. And then the quality at 3 is going to end up as a saturated vapor, which is going to be a quality of X equals 1. We're told that process 3 to 4 has constant volume cooling to T4 equals 160 degrees Celsius. So we're going to have T4 equals T1 is 160 degrees Celsius. And that makes sense because process 4 to 1 has isothermal expansion. Once again, T1 equals T4. And we're going to have a Q41 of 815.8. So we can fill that in up here. Now with all the obvious numbers filled in, let's take a look at what else we can fill in. So process 1 to 2 has a constant volume heating. So that means that because we're heating, that means that heat must enter the system, so the heat must be positive. Now, what else can we infer is that because you have a constant volume, you have no work. If you have no volume, no change in volume, you have no work. So we have 1 to 2's work is going to be equal to 0. And next, if you look at process 3 to 4, same thing. You have a constant volume, so that means that the work is also equal to 0. Process 2 to 3 says that we're cooling, so that means that heat's leaving the system, so the heat should be negative there. And then same thing with process 3 to 4, we're going to have a negative heat transfer there. And last but not least, remember that this cycle is going to maintain equilibrium, so that means that the net cycle's change in internal energy is going to be equal to 0. So now that we've went through all of our assumptions here, I'm going to go ahead and start at state 1's pressure of 5 bar and 160 degrees Celsius in order to get the remaining properties. So what we have at 1 is we have 5 bar at 160 degrees Celsius, so let's check out where we are on the properties table. If we go to 5 bar on the property table, table A3 for water, we have a saturation temperature of 151.9 degrees Celsius. We're working with 160 degrees Celsius, so that means that we're in the superheated region. And I'm going to go ahead and fill it in the table over here so we can keep track of everything. So now the next thing I want that volume and I want the internal energy. So to get those, I'm going to have to go to the superheated region or superheated table in the properties table for the specific state at 1. So here we are at table A4 for water. So if you go to 5 bar of pressure and you see you don't have a temperature of 160 degrees Celsius, you'll have to do some linear interpolation. And if you do linear interpolate, you'll find that the specific volume at 1 is going to be equal to 0.3841, and that's going to be cubic meters per kilogram. And the change in, or the internal energy, I should say, is going to be, specific internal energy is going to be 2576.5, and that's going to be in kilojoules per kilogram. I personally chose to interpolate between, or not between, but underneath 180 and 200. You could have also interpolated from the saturation temperature in 180 and you would have taken the in-between value. So let's make sure we keep track of everything we have here. So we have a superheated property or a superheated quality at 1. We have a specific volume of 0.3841 cubic meters per kilogram. And we have an internal energy, a specific internal energy of 2576.5 kilojoules per kilogram. And I went ahead and reflected those properties into the table down here. So next up, I'm going to work on state 2. So at state 2, you're getting that you have 10 bar, and if it looks like you have nothing else here, but remember that in the problem statement, it does say that from 1 to 2, you do have a constant volume heating. So that means that V1 is going to be equal to V2, which is going to be equal to 0.3841. Also, before I move forward, I should have mentioned that the volume in this case is just going to be equal to the specific volume because you have a mass of 1 kilogram. So remember that volume is going to be equal to specific volume times mass, which would be equal to 0.3841 meters cubed per kilogram times 1 kilogram would just give you 0.3841 cubic meters. So that's where I got that volume from in state 1. Now in state 2, it's going to be equal as well. So you're going to have 0.3841 for state 2. And that means that not only the volume, but also the specific volume is going to be equal. So now that I have 10 bar of pressure and 0.3841 meters cubed per kilogram for a specific volume, now we can go into our properties table and figure out where we are. So at table A3, we have our saturated table here. So if you go to 10 bar and you see you have 1.1273 meters cubed per kilogram for your fluid specific volume, and then you have 1944 for your saturated vapor specific volume, we were at 0.3841, which is far greater than the saturated vapor specific volume, so we're once again in the superheated region. So I'm just going to reflect that both up in the list up there, as well as in the table down here. And now I still need my internal energy from state 2, and I'm also just going to get the temperature as well because we're going to need a TV diagram. So we'll go to our superheated table since that's the state that we're in. So you go to 10 bar, that's where we are, so 10 bar over here. And then we were at 0.3841 of a specific volume, which is going to be between these two numbers right here. So the number that we get is going to be somewhere in between these two numbers for both temperature, specific volume, and internal energy. So now if you interpolate using your pressure and your specific volume, you'll have the specific internal energy at 2 is going to be equal to 33.98 kilojoules per kilogram. And as you can see, that number is right between these two numbers over here. And then your temperature is going to be between 540 and 600, and it ends up being T2 equals 563.83 degrees Celsius. So I just went ahead and filled in the table, or the list up here, as well as what we have in the table down here. All right, so next up at state 3, we have 10 bar as well as a quality of 1, so a saturated vapor. So we can just go to our saturated tables, obviously, because we're in saturated vapor region. And here we are at 10 bar and x equals 1. We'll have a specific volume of 1944, and we'll have a specific internal energy, saturated vapor, 2583.6 kilojoules per kilogram. And I almost forgot, we also need the temperature, which is 179.9 because you're at the saturated state. So again, you're going to have the volume, specific volume at 3 is going to be equal to 0.1944 cubic meters per kilogram. You're going to have a specific internal energy of 2583.6 kilojoules per kilogram. And lastly, you're going to have a T3 temperature of 179.9 degrees Celsius. And just remember that in this case, the volume is going to be equal to the specific volume times the mass, which is going to be equal to 0.1944 times 1, which is going to be equal to 0.1944, and the unit would be meters cubed. Now, at state 4, you have 160 degrees Celsius, but in addition, you also are told that process 3 to 4 has a constant volume cooling, so that means that V3 is going to be equal to V4. All right, so now with these two values, we can go into our properties table. Let's start at the saturated table. So at table A2, if we go to 160 degrees Celsius, we have a saturated liquid specific volume of 1.102 and a saturated vapor specific volume of 0.3071. So we have a specific volume of 0.1944, which is going to be in between these two numbers. So therefore, we are working with a two-phase mixture. So let's find the phase status of this two-phase mixture. So if we use the formula of X is equal to V4 minus VF divided by VG minus VF. So I went ahead and just plugged in what we have. So we have V4 as 0.1944, again, because V4 equals V3, and then we have the saturated fluid or saturated liquid specific volume from right over here. Remember, you have to divide it by 1,000. And then you also have the saturated vapor specific volume of 0.3071. If you plug all this in your calculator for x4, you're actually going to get that x4 is going to be equal to 0.6317. So now we can use this quality here to find the internal energy, the specific internal energy at 4. So to find the specific internal energy at 4, we're going to use this formula here that just has the specific internal energy at 4 being equal to the specific internal energy of a saturated liquid plus the quality times the difference of the specific internal energy of a saturated vapor minus saturated liquid. So to find UF and UG, we're going to look at these two numbers right over here. So that's going to be your UF, and here is going to be your UG. So U4 is going to be equal to 674.86 plus 0.6317 times 2568.4 minus 674.86 kilojoules per kilogram. You'll have that U4 is going to be equal to 1871.01 kilojoules per kilogram. Now the last thing that we're missing is just that pressure at state 4, which again, we were in the saturated table, so that just means that our pressure 4 is 6.178 bar. So now that we just solved for all of the properties of each state, we can now find the work, heat transfer, and change in internal energy of each process. And this is going to be nothing more than just repetitively using the first law of thermodynamics. So at process 1 to 2, you're going to have that the change in internal energy from 1 to 2 is going to be equal to the heat transfer from 1 to 2 minus the work from 1 to 2. Remember that we can break down this unit here equal into its specific components. So we'll have that the mass times the difference of U2 minus U1 is going to be equal to the heat transfer minus the work. Now once again, remember that because 1 to 2 had constant volume, we had our work being equal to 0, so we can go ahead and cross that right out. And we're going to have that our heat transfer is going to be equal to our change in internal energy. And luckily for us, we already have all of our specific internal energies right over here, and we have a mass of 1 kilogram. So we're just simply going to have that the heat transfer from 1 to 2 is going to be equal to 1 kilogram times the difference of 33.98 minus 2576.5 kilojoules per kilogram, which will just give you kilojoules. So you're going to have Q1 to 2 is going to be equal to 657.48 kilojoules. And that makes sense that it's positive because once again, it's a heating process, so heat enters the system. And once again, remember that we had Q12 is equal to the change in internal energy because you have no work, so these two numbers here are going to be equal. When you're reading this processes table, just remember that the middle column minus the left column should always equal the right column. So in other words, Q 657.48 minus W0 equals change in internal energy 657.48. So now in the case of process 2 to 3, we once again have that the change in internal energy is going to be equal to the heat transfer minus the work. In this instance, notice once again you can break down the unit of the change in internal energy into the specific units because we already have all of that, and then the work can be calculated using a formula. So you'll have the mass times the difference in specific internal energy is going to be equal to the heat transfer 2 to 3 minus the integral from V2 to V3 PdV. Now, if you evaluate this integral, you're going to have that the mass times the change in specific internal energy, once again, is going to be equal to the heat transfer from 2 to 3 minus the pressure times V3 minus V2. So now this is all stuff we can work with. We just plug in our numbers. And we're going to have the mass as 1 kilogram, U3 is 2583.6, U2 is 3233.98. You're still going to solve for your heat transfer, and then your pressure, pay attention to this instance that you're going to have 1,000 here rather than 10. Because we have to keep our units consistent to get kilojoules, we're going to be using kilopascals instead of bar. So you just have to multiply the bar times 100 to get into kilopascals, and then your difference of volumes right over here. And if we evaluate one step further, you're going to have that your change in internal energy is going to be equal to negative 650.38 kilojoules, and your work is going to simplify into negative 189.7 kilojoules. And when you solve for Q23, you're going to have it equal to negative 840.9 0.08 kilojoules. Now at process 3 to 4, we can once again apply our first law of thermodynamics. Notice that you have a constant volume process here, so once again, we can cancel out our work. And you're going to be left with that the heat transfer is going to equal to the change in internal energy. I'm just going to break down the change in internal energy once again. Then I'm going to plug in our numbers for the change in internal energy, and if you plug in your calculator, you'll have negative 712.59 kilojoules. And because the work is equal to 0, this is also going to be equivalent to the change in internal energy. And finally, at process 4 to 1, you have U41 is equal to Q41 minus W41, just the first law again, break it down, and you have the mass times the change in specific internal energy is going to be equal to the heat transfer, which is given as a positive number, 815.8 minus the work. Solve out for your change in internal energy, and you're going to have 705.49 positive, minus is going to be equal to the heat transfer minus the work, and the work will be calculated to 110.31 kilojoules. So now if we just do the summation of each of these columns for the work and the heat transfer, we can find the cycle work and cycle heat transfer. And if you do that, you're going to have negative 79.39 for the work and negative 79.39 for the heat transfer. And that makes sense because once again, if you have the heat transfer of negative 79 minus a negative 79, so basically plus 79 for work, you're going to have 0 as your change in internal energy. And notice that the summation of the change in internal energy column is also going to be equal to 0, so this all makes sense here. Now to find the thermal efficiency of this cycle or this system, just look at the heat transfer column here and notice that you have a negative cycle heat transfer, so that means that what we're working with here is actually going to be a refrigeration cycle. So if the goal of this process is to actually refrigerate the target system, then we're going to be having a refrigeration cycle, and if the target here is supposed to just maintain at a certain temperature, then we have a heat pump cycle. So to find the coefficient of performance of a refrigeration cycle, you're just going to have the total heat entering the system divided by the cycle work of the system. So in this case, we're going to have 657.4 plus 815.8 because those were the heat transfers entering the system divided by the net work. Take the absolute value of everything, and you'll have that the coefficient of performance would be 18.56 if you're looking at a refrigeration cycle. Now, if you're looking at a heat pump cycle, it's a little similar, but the difference is that you're going to be using the Q out rather than the Q in, and that will net you with 19.596 as the coefficient of performance for that instance. And now, last but not least, we were asked to find two tables or charts. We were asked to find the TV diagram and the PV diagram. So I'm going to start with the TV diagram. So on the y-axis, we'll have the temperature in degrees Celsius. And on the x-axis, we will have the specific volume in cubic meters per kilogram. So now we just have to point plot. So you know that at state 1, you had a 3841 meter cube per kilogram specific volume, and you had a temperature of 160 degrees Celsius. So we're going to plot that as 0.1. And then at state 2, you were heated all the way to 563.83 degrees Celsius, and you also had the same specific volume. The volume was constant, so you had 0.3841. So you can bring that right above to right about there, and we'll call that 563.83 degrees Celsius, and you can connect the dots, so 1 to 2. Next, at state 3, you were at 0.1944 meters cubed per kilogram, so we'll call that right about there, 0.1944. And your temperature at state 3 was 179.9, so we'll call that right about here, 179.9, and then we can make a dot here, and we connect the dots. Finally, at state 4, you had 160 degrees Celsius and 0.1944 meters cubed per kilogram, so you can go ahead and draw that right over here. It should be horizontal to 1. I know that my graph here is not the best, but just know that 3 to 4 should be vertically down, and 4 to 1 should be horizontal. Remember that 1 to 2 should be vertical because you had no work from 1 to 2, and same thing with 3 to 4, it should be vertical because you had no work, and you can't take the area under the curve because there is no work. Now finally we can do our PV diagram. So we'll have the pressure on the y-axis and we'll keep it in bar. And we'll have our specific volume once again on the x-axis in meters cubed per kilogram. So now all we have to do is plot our points once again. So at state 1, you had 5 bar and 0.3841 specific volume. So that's right about here. And then at state 2, you were still at that same specific volume and you were at 10 bar. So if you move directly upwards, you should be right about there. And then at state 3, you had 0.1944 specific volume and 10 bar of pressure. So that should be vertically above the 1944, horizontally with the 10 right about there. And then at state 4, you were at 6.178 bar and 0.1944, which would be directly below right over here. Now we just connect the dots. And just like that, we have our PV diagram labeled from 1 to 2 to 3 to 4. And because it's a refrigeration cycle, you see that it's actually going counterclockwise. A power cycle would have actually went clockwise. So it seems that this problem statement mislabeled as a power cycle.